Good morning, all. In today's class, we'll mainly deal with a brief overview of the properties of Laplace transform, as well as the relationship between Fourier transform and Laplace transform. In the last class, we had a brief introduction to the Laplace transform. Just rewinding that what we have taken in the last class, we mainly took what are the formulas of Laplace transform, the inverse Laplace transform formula, the two different types of Laplace transform, that is unilateral and bilateral Laplace transform, the concept of region of convergence or ROC, some of the features of Laplace transform, details about S-plane, as well as the significance of poles and zeros in the S-plane. So today we'll be just seeing the overview of the properties of Laplace transform. We know that Laplace transform has replaced Fourier transform in a sense that we can take the Laplace transform of many of the functions for which Fourier transform cannot be applied. And we usually represent the Laplace transform in S domain of the form x of t in time domain. If you are taking its Laplace transform, it will give you the Laplace transform as x of s. And if suppose y of t is the time domain function, its Laplace transform is indicated by y of s. So here mainly we'll be just dealing with an overview of the properties. We are mainly dealing with some 14 properties. The first property is linearity, and the basic Laplace transform pair is given by a x of t plus b y of t. Laplace transform will give you a into x of s plus b into y of s. The time shifting property is the next one, which indicates x of t minus t naught. Laplace transform will give you x of s into e raised to minus s t naught if t naught is greater than 0, and x of t plus t naught Laplace transform will give you x of s into e raised to s into t naught when t naught is less than 0. The third property is frequency shifting property, which indicates x of t into e raised to s naught of t. Laplace transform will give you x of s minus s naught. Next is the time scaling property, that is x of at. If you are taking the Laplace transform, it will give you in the frequency domain 1 by a x of s by a, for which the scaling factor a is greater than 0. Frequency scaling is given by 1 by a x of t by a will have a scaled version in the frequency domain, that is capital X of as. Next one is time differentiation, that is d by dt of x of t Laplace transform will give you s x of s minus x of 0 minus. This x of 0 minus is the initial condition which will be further used for solving the differential equation using Laplace transform. Next property is time integration property, which indicates 0 to t x of tau d tau. Laplace transform will give x of s by s. Next property is time convolution x of t, convolution y of t. Laplace transform will give x of s into y of s. That is multiplication in the time domain is convolution in the time domain is equivalent to multiplication in the frequency domain. Complex differentiation property is given by minus t x of t. Laplace transform will give you d by ds of x of s. Complex frequency shifting will give you e raised to s naught t x of t. Laplace transform will give you x of s minus s naught. Conjugation is given by x star of t in the time domain gives you Laplace transform x star of minus s. Initial value theorem and final value theorem, which is of very high importance, that is if suppose x of t where t tending to 0, that is if suppose t is equal to 0, this is denoted as x of 0, it will be Laplace transform to limit of s tends to infinity s into x of s. Final value theorem is limit of t tends to infinity x of t Laplace transform giving you limit of s tends to 0 s into x of s. The multiplication or modulation property, it is given by suppose x1 of t and x2 of t are two signals. On multiplying it in the time domain, it is equivalent to performing convolution in the frequency domain. And these are the special cases of time differentiation property. That is, this we have already dealt with. D by dt of x of t is s into x of s minus x of 0 minus. Similarly, if it is of higher order derivatives, that is d square by dt square x of t, that will be transformed as, here it is square, that is 2 is the degree, so it will be s square x of s will be the starting, and minus s into x of 0 minus. This x of 0 minus is the initial condition, and minus d by dt of x of 0 minus. Similarly, it can be generalized as, if suppose it is d raised to n, here n is equal to 2, if suppose it is d raised to n by dt raised to n x of t, then it is Laplace transformed as s raised to n x of s minus s raised to n minus 1 x of 0 minus etc etc. Okay. And then we'll take the derivatives of the initial condition. So this is just a brief overview of the properties of Laplace transform. Now moving on to the next topic, that is the relationship between Fourier and Laplace transform. In the last class itself, we have told that the Fourier transform is usually expressed as a continuous sum of exponential functions of the form e raised to j omega t. And there is chance of occurrence of convergence issues in the case of Fourier transform. That is, there is chance that if you are taking x of t alone, the function may not be absolutely integrable, thereby violating the Dirichlet's condition. Hence, Fourier transform does not exist for many of the signals due to this limitation of not absolutely integrable. Moreover, it cannot be also used to analyze the unstable system. There came the solution for this kind of problem, which was found by the French mathematician Marcus Pierre-Simon de Laplace, who developed a new transform technique which overcome the problem of convergence of CTFT. Hence, Laplace transform can be used as an alternative of Fourier transform, where the Fourier transform cannot be used. In the case of Laplace transform, it includes an exponential convergence factor, sigma, along with j omega, because we know that it is, in Laplace transform, it is the S domain we are considering. So S is represented as sigma plus j omega. This j omega was only present for CTFT. So in Laplace, we are again introducing a new term sigma, which is called as the convergence factor. So instead of representing it as the sum of complex sinusoids, in Laplace transform, we represent it as a sum of complex exponentials in the form of e raised to st, where s is the complex frequency of the form s is equal to sigma plus j omega. And since we are including this convergence factor sigma, the x of t into dt, it becomes absolutely integrable, and hence Laplace transform exists for many of the functions for which Fourier transform does not exist. It is due to this function sigma. We know that the Fourier transform of a continuous time function x of t, it is defined as x of omega is equal to integral over minus infinity to plus infinity x of t e raised to minus j omega t dt. This is a known equation. This can be either x of omega or x of j omega. And its inverse Fourier transform equation is given by x of t is equal to 1 by 2 pi integral over minus infinity to plus infinity x of omega into e raised to j omega t d omega. Mark it as equation number 1 and equation number 2. So this is actually the CTFT format. Now you are going to convert it into the Laplace format by including the convergence factor sigma to this equation. That is, the equation of x of omega, that is equation number 1, it can be changed in this form. That is, including convergence factor by replacing omega by sigma plus j omega, we can express this equation 1 as x of sigma plus j omega into is equal to integral over minus infinity to plus infinity x of t into, it was just minus j omega t, it can be, sigma can be also added. So e raised to minus sigma plus j omega t dt. So here you are just adding sigma to both the LHS as well as the RHS side, and that is marked as equation number 3. In the similar fashion, equation number 2 of x of t may be also represented like this. That is, wherever you find omega, it can be replaced by sigma plus j omega. So equation of x of t becomes 1 by 2 pi integral over minus infinity to plus infinity x of sigma plus j omega into, this was e raised to j omega t. It is replaced by sigma plus j omega t d omega. So we already know that the sigma plus j omega is nothing but equal to s. Okay, the complex frequency factor. Hence, on differentiating s with respect to omega, we get it as this RHS is written here, ds by d omega is equal to j, because this sigma is a constant. So on in differentiating it with respect to omega, we get it as j, so that this d omega in equation number this 4, it can be replaced by, on rearranging the equation, we get it as ds by j. Okay, so this is what you are going to substitute. This equation number 5, it will be substituted in the above two equations, that is equation number 3 as well as equation number 4. We will substitute sigma plus j omega is equal to s, and we will substitute for d omega, which is obtained by rearrangement. And we get x of s as, that is, this was x of sigma plus j omega in equation number 3. It becomes x of s is equal to integral over minus infinity to plus infinity x of t into e raised to minus st dt. That is your equation number 6. And x of t is equal to 1 by 2 pi j integral over sigma minus j infinity to sigma plus j infinity x of s e raised to st into ds. We will just substitute, okay, from equation number 5. Hence, equation 6 and 7, they constitute a complex Fourier transform pair or bilateral Laplace transform pair. Hence, we can say that Laplace transform is nothing but a complex Fourier transform. On comparing with the standard equation, you get this result. That is, Laplace transform of x of t is the Fourier transform of x of t into e raised to minus sigma t. This was already discussed in the previous class. That is, Laplace transform means it is a Fourier transform of x of t into e raised to minus sigma t. If x of t is absolutely integrable, then Fourier transform of x of t is obtained by Laplace transform by using the relation x of omega is equal to x of s, where s is given the value j omega. We know that if you are giving, instead of s, if you are giving j omega, in this equation, if you are giving, instead of s, if you are giving j omega, we will get x of t into e raised to minus j omega t dt, which is nothing but the equation of Laplace Fourier transform. So on substituting s is equal to j omega, we get the Fourier transform. That is, Fourier transform is the Laplace transform along the imaginary axis of s plane. We know that imaginary axis is nothing but the j omega axis. So if you are giving s is equal to j omega, then Fourier transform we get, it is the Laplace transform along the imaginary axis, that is the j omega axis of the s plane. So this is all about the relationship between the Fourier transform and the Laplace transform. That's all. Thank you.